apply this technique to this situation. But first of all, when do we use polynomial division? We use a division like we've just done, the one we've just looked at in other words. Why do we need this division technique in red here? Because the top number was bigger than the bottom number. It's a top-heavy fraction. So the first thing to do is to recognise that this is a top-heavy fraction algebraically, and it is a top-heavy fraction because if I multiply out the numerator, I get this: x cubed plus 2x squared plus 4x over x squared plus 2x plus 1 is what we actually end up with. Why is that a top-heavy fraction, do you think? Yeah, I've got a higher cubic on the top than I have on the, sorry, higher polynomial on the top than the bottom. So cubed on the top, squared on the bottom. That makes it top-heavy. So if my highest power of x on the top is greater than it is on the bottom, it's a polynomial. It's a top-heavy fraction. And to simplify this, we use polynomial division. So let's have a look and see how we apply that now. What we're going to do is to divide the denominator into the numerator. So we write down a division, literally. Now we want to know, and this is the key step really, what we ask ourselves now is, what have I got to multiply this by to get this? I take each one in turn, like we did in the long division. How many lots of this are there in this as we go along? And what we do is we focus on just the highest power of x, x squared, and ask ourselves the question, what have I got to multiply x squared by to get x cubed? Answer, x. Because x squared times x is x cubed. So, how many times does this go into this, but this part of this whole thing? How many times does this go into this? Focus on this bit and this bit. The highest power in the denominator and the highest power in the numerator. What have I got to do to x squared to get x cubed? Multiply by x. So that's what goes at the top. And then I say to myself, well, what is x times, what is x times this? So as a little aside, I can work out what x times x squared plus 2x plus 1 is. It's x cubed plus 2x squared plus x. And that's what x times this is, so that's what goes underneath. X cubed plus 2x squared plus 2x. Think back to the division. When we looked at that division, once you've got it, it's quite straightforward. What did I do? How many 23s are there? For example, we said, how many 23s are there in 142? Well, 6. In this particular example, what have I got to times x squared by to get x cubed? X. And that's what goes at the top. And then I ask myself, well, what is x times this? It's this. Now I need to work out the remainder, so I'll put it underneath. Notice that these are the same. They have to be the same. I made them the same. That was the whole point. I asked myself the question, what have I got to do to this to get this times by x? The whole point of asking myself that question was so that these were the same, and when I do the subtraction to find the remainder, they disappear. If they don't disappear, you didn't multiply this term by the right thing. You didn't multiply by the right thing. So if they don't cancel out, you've gone wrong. I work out the remainder now. This will always be naught. The rest doesn't have to be naught. It's coincidence that in this particular example 2x squared minus 2x squared is nothing. But 4x minus x is 3x. So remainder 3x. So now I bring down the next term. Well, there isn't a next term. And so my answer is what? My answer is the original fraction x cubed plus 2x squared plus 4x over x squared plus 2x plus 1 is equivalent to what? Well done, Luke. Exactly right. So I can rewrite this like this.